In this lesson, we are going to discuss relationships between quantitative variables, and we're going to discuss how to display these things graphically. Remember that quantitative variables are things that can be represented by numbers versus categorical variables where the variables are category names. So first, a scatterplot is a two-dimensional graph of the measurements for the two numerical values. This displays the relationship, if any, between the two quantitative variables. So, scatterplot. It looks like a bunch of points scattered in the plane. The correlation is a statistic that measures the strength and direction of the linear relationship between the two variables. So, correlation. And the regression equation is an equation that describes the average relationship between a response and explanatory variable. So remember that the response variable is the y variable and the explanatory variable is the x variable. The response variable we sometimes also call the dependent variable, and the explanatory is called the independent variable. Now in a scatter plot, the response or dependent variable is plotted on the y-axis, and the explanatory variable or independent variable is plotted on the x-axis. So when you have a scatter plot, some of the things to ask yourself, first of all, is what is the average pattern? Is it a straight line? Or is it curved? So for example, you might expect height and weight to more or less be a straight line as height increases, weight increases, but something like temperature versus time of year would definitely display a curved pattern. The next thing you'd like to ask is, assuming you have a straight line, what is the direction of the pattern? Do the points tend to go up together or down together? Another question to ask is, how much do individual points vary from the average? So how spread out are those points? And are there any unusual points that don't seem to fit with the bulk of the data? These might be something called an outlier. So two variables have a positive association when the values of one variable tend to increase as the value of the other variable tends to increase. For example, height and weight. So that's a positive association. Two variables have a negative association when the values of one variable tend to decrease as the values of the other variable increase. For example, your time in a race and miles run. The more you run, the faster you get and the lower your time gets. So as your miles run increases, your time decreases. And two variables have a linear relationship when the pattern of the relationship resembles a straight line. For each of the following examples, is there a positive association, negative association, or no association? So the first graph shows us the height of a subject in inches and their hand span in centimeters. And you can see that for people that have bigger heights, they also have bigger hand spans. This is an example of a positive association. As height increases, hand span also increases. In the next graph, we are looking at the age of a participant and the distance that they can first see a sign in feet. So for example, this probably 18-year-old participant can see a sign when it's 500 feet away approximately, versus this almost 75-year-old person for whom it's something like 100 feet away, which they can see the same sign. So this is obviously a negative association. And you see that as age increases, the maximum distance at which one can see a sign decreases. So as age goes up, distance goes down. For each of the following pairs of variables, is there likely to be a positive association, a negative association, or no association? So the amount of alcohol consumed and performance on a test of coordination, where a high score represents better coordination. So imagine a graph. On the x-axis is our explanatory variable, so amount of alcohol. And the y would be the coordination. And you would expect that in general, the coordination will go down as the amount of alcohol increases. This will be a negative association. Height and grade point average. Well, if you were to say graph height and GPA, so we'll call height the explanatory and GPA the response, and you're going to have people of various heights having GPAs all over the place. So this will very likely be no association. And then weight of a car and average number of miles per gallon. So we'll have weight as the explanatory, MPG as the response, and heavy cars tend to get worse gas mileage, so you're going to have some variability, but on average, as the weight increases, the MPG goes down. So this is a negative association. A linear pattern is common, but it's not the only type of relationship. Sometimes a curve describes the pattern of a scatter plot better than a line does. And if so, that relationship is called nonlinear or curvilinear. So for example, if I graphed time of year and temperature, it's going to look something like this. And there's a great obvious predictable pattern there. Things are going to sort of cycle semi-predictably with some wiggly noise around it because the temperature in January is not always below zero. But if you assume that the relationship was linear, technically you would see that there was no relationship at all. So you should always look at the scatter plot to see if the relationship could be linear. Now the figure for this exercise is a scatter plot of average math SAT scores, that's our response variable, versus the percent of graduating seniors who took the test that year, and this is for all 50 states and the District of Columbia. So what you can see is that as the percent taking the test increases, the average math SAT score tends to go down. So this is a negative association. And let's just give a little explanation. And that can just be as the percent of students taking the test goes up. The average SAT math score goes down. And that might seem strange until you realize that there is more than one standardized test that one uses to get into a college. So for example, where I'm from, we actually use the ACT, not the SAT. And in that case, the people who took the SAT where I was from were people that were only applying to selective schools that did not use the ACT but used the SAT scores. So you might just have a small subgroup of really good students taking the test when the percentage is low. They might all be great students applying elsewhere, versus a state in which that test was used for lots of different people. You're going to see that the average goes down because a larger variety of people take the test in the first place. Explain whether you think the pattern of the plot is linear or curvilinear. So do the points more or less fall in a straight line? So try to imagine a line going through those points. And maybe that's okay, but you could also imagine that perhaps there was some kind of exponential decay-like curve there going on. So you can justify this either way. I think it's wise to say that the points are pretty much linear, but might be a little bit curved. So the points fall into a linear pattern. Possibly with slight, we'll use a fancy word, curvature. Curvature. So approximately what was the highest average math SAT for the 50 states and District of Columbia? Approximately what percentage of graduates took the test in that state? So that's this point right there, just a hair over 600. So we'll say it's about maybe 605, 610. So we'll say about 605. And if we drop down, we see that perhaps 5% of graduates in that state took the test. So about 5% of graduates took the test in this state. About what was the lowest average math SAT for the 50 states and District of Columbia, and about what percentage of graduates took the test in that state. So that is this point down there. That looks like the score is approximately 475. So the lowest average was about 475. And looks like approximately 60% of graduates took the test in that state. Identify whether a scatterplot would or would not be an appropriate visual summary of the relationship between the following variables. In each case, explain your reasoning. So for a scatterplot to be an appropriate visual summary, the kicker is that both of your variables must be quantitative. Okay, so blood pressure and age, are both of those variables quantitative? Yes, both variables are quantitative. And just for kicks, you could ask yourself, is it likely to be a positive association, negative association, or none? So as age increases, what tends to happen to blood pressure? On average, it tends to go up. So this will probably be a positive association. So religion of country and opinion about stronger gun control laws. Are those variables quantitative? And the answer is no. So no, a scatter plot is not appropriate. The variables are categorical. In that case, you might want to revert to a histogram or something instead, or pie charts. Now, it's also useful to know how to use technology to create scatter plots, because really, who wants to draw axes and plot points? And this is something we have technology, we should totally use it. So your book comes with data sets, and in your note sheet, you have the web page for this data set, and you can go there and you can download the data from this data set. So directions are given on that note sheet. And I chose to do this in Excel because I think that's what you will use most frequently. So the first thing you do when you're downloading that data, you need to input the data into Excel. And if you're not using Excel, that's fine. There's Numbers on the Mac. There's a program that's free called OpenOffice, which is quite similar. The specifics of all these specific programs, unfortunately, are a little bit tedious, and I'll give you general directions that will work for lots of stuff, but you might have to do a little bit of Googling or asking for help to get this for yourself. So first, input the data into Excel. And the second thing you do is you highlight the X and Y columns. You select Charts, and then you choose Scatter. And here you're going to get something that looks like this. You see as on the bottom axis X, that is the latitude, and on the Y axis is the average August temperature. And you can see that for places that have high latitudes, they have lower temperatures, which should make sense. As you get closer to the poles, the average August temperature is lower than in places that are closer to the equator. So is this pattern linear or curvilinear? And then what is the direction of the association? So you can probably imagine a line passing through this data, more or less. So I think it's pretty obvious here that the pattern is linear. So it's a linear pattern, and is the association positive or negative? It's definitely a negative association. And you can say that as latitude increases, the average August temperature decreases. Are there any cities that appear to be outliers? If so, which cities are they? So you can look at the chart and you can see that maybe this guy up there is sort of not with the picture. That is Phoenix. Whoops. So you say maybe Phoenix. But I would say you could argue this one either way. There really aren't any obvious outliers. Like maybe this point down there, but he's not too far off either. Okay, now that we have some tools to deal with scatter plots, our question is well, how do we find that line that sort of fits and goes through the best points? So the area of statistics that is used to examine the relationship between quantitative response variable and one or more explanatory variables, that is called regression analysis. So we are going to focus on the one explanatory variable case, but it is definitely possible to do 3, 4, 5, 6, 7 explanatory variables. Now, the regression equation describes how, on average, the response variable is related to the explanatory. And a linear relationship is a straight line relationship. You should always look at the scatter plot of the data to see if a linear relationship is a reasonable model. Don't assume things are linear. And finally, the regression line. This is the straight line that best describes the linear relationship between two quantitative variables. Now we'll talk more about what that best means in a little bit. So hopefully from a previous math class like Algebra 1, you remember the equation for a straight line. A line with slope m and y-intercept b has the equation y equals mx plus b. Now, just to be a little bit different, so to say we have a regression line, we usually use y with a little hat on top. That's read y hat. And instead of m and b, we use b sub 0, which is read b naught plus b1x. And this is partially because when you start to look at having more than one explanatory variable, you'll have b naught, b1, b2. You could have b naught, b1, b2, b3. So, but b naught always refers to the y-intercept. So suppose that we have a regression equation for the relationship between weight in pounds and height in inches for men 18 to 29 years old, and it's given by y hat equals 6x minus 250. Estimate the average weight for men in this age group who are 70 inches tall. To do this, we just input 70 into the equation. So y hat of 70 is equal to 6 times 70 minus 250. Well, 6 times 7 is 42. Add on your 0. So this gives us 170 pounds. So that tells us that on average, men who are 70 inches tall weigh 170 pounds. You will often have to summarize the things that you're doing into sentences, just because part of the purpose of this class is to teach you how to interpret things and communicate them properly. And then also note that this, you have to really say on average, because this doesn't mean every single 70-inch tall man weighs 170 pounds. Of course, that's not true, but if you look at all the guys who are 70 inches tall, of those guys, the average weight in that group is going to be 170 pounds. What is the slope of the regression line for average weight and height, and what does it mean? So first of all, slope is with the x, so the slope is 6. Everyone should know that much. Also, remember that slope comes from this equation that's y2 minus y1 over x2 minus x1, which I'm going to call capital delta y over capital delta x for change in y over change in x. And then think about what y is measured in. Y is measured in pounds. X is measured in inches. So what you have is this slope is 6 pounds per inch, or if height increases by 1 inch, that's the delta x change, weight increases by 6 pounds on average for men in this age group. And it doesn't hurt to be a little bit specific, because this regression line was found for men 18 to 29, and the fact that it was men, women probably are going to be different. So specify what group of people you are talking about. What group of people is your population? Another example, a study was done in which researchers measured the maximum distance at which an automobile driver could read a highway sign. 30 drivers participated. The regression line y hat equals 577 minus 3x. This describes how the maximum sign legibility distance, the y variable, is related to the driver age, the x variable. This is the example where we saw a picture for it in actually example 1. So first of all, what is the slope of the equation? And what does it mean? Remember, slope is with the x. So this one I switched up on you to just see if I can trip you up. The slope here is -3. The negative does matter. That means we have a negative association. So recall, once again, this is delta y over delta x. And y's units are, so sign legibility distance, that's probably measured in feet, per x, which is probably measured in year. So this means that the distance at which you can see a sign goes down about 3 feet per year. Or we could say for every year older a participant is, the maximum distance at which they could read a sign decreased by 3 feet. And don't forget those 2 magic words, on average. It is possible to be a young person with terrible eyesight, and it's possible to be an older person with good eyesight. But on average, as people age, the distance that they can see does tend to decrease. Let's use this regression equation to predict the sign legibility distance for people aged 30, 60, and 90. So how I'm going to represent that is I'm going to put y hat parenthesis 30, which tells me that I'm plugging 30 into y hat. So that's 577 minus 3 times 30, or 577 minus 90. So for a 30-year-old, they can see on average 487 feet. Y hat of 60, this is 577 minus 3 times 60, or 577 minus 180, which is 397 feet. So on average, 60-year-olds see a sign at 397 feet away. And for that 90-year-old, on average, 577 minus 3 times 90 is 577 minus 270. Tells us that it's at 307 feet. Now, lastly, if someone can see 500 feet, approximately how old are they? Well, in this case, we're going to put 500 in for y hat. So 500 equals 577 minus 3x. Solve that for x, so take away 577 from both sides of the equation. And then we have minus 77 equals minus 3x. And if you divide by -3, you have 77 over 3. And that's not super helpful, so let's get a decimal. This is approximately equal to 25.6 repeating, or we'll say, well, it's actually exactly equal to 25.6 repeating, so let's fix that. X is approximately equal to 25.7 years. So if someone can see 500 feet, you'd expect them to be approximately 25.7 years old.